everyone, welcome back to Minute Science Marvels, where we break down the wonders of science into bite-sized episodes. This week, we're diving into quantum computing with our deep dive, real-world application, and fun facts. If you've been following along on my TikTok, you probably saw the This Week in Science segment about Google Willow's quantum chip. It sparked a lot of questions. And what I love about science is that sometimes the answers just lead to more questions. People ask what kind of problems they solve, what things like random circuits are, and even just how quantum computers work. So I figured it's time for a full breakdown. We're going to simplify everything together. To understand quantum computing, let's first compare it to the computers that we use every day. Bits are the building blocks of every operation in a regular computer. They're used everywhere, from processing data to storing information. For data processing, every app or program you use, whether it's calculating a number, streaming a video, or playing a video game, relies on bits to execute its instructions. Each instruction is converted into a sequence of zeros and ones that the computer's processor can understand. For storage, when you save a file, it's stored on a hard drive or a memory disk as a sequence of bits. Each bit represents either a 0 or a 1, encoding texts, images, music, any kind of digital data. Bits are also the language of computer networks. When you send an email, browse a website, watch this video, bits are transmitted across the internet to deliver your information. Regular computers process information using bits, which are like tiny switches that can be either off, 0, or on, 1. Each problem they perform follows a really specific sequence. So there's a step 1, step 2, step 3. All of it's really clear and methodical. Quantum computers, on the other hand, take a completely different approach. They use qubits. What makes qubits special is a quantum property called superposition. A qubit can be a 0 or a 1, or both at the same time. Like when you flip a coin, while it's spinning in the air, it's not heads or tails, it's potentially both. That's what superposition allows in quantum computing. Another good example is one of the most famous thought experiments in quantum mechanics, Schrodinger's cat. So if there's a cat sealed in a box with poison that's triggered by a quantum event, like the decay of an atom, the cat is either alive or dead. These are two separate, very distinct outcomes. But in the quantum world, until you open the box and observe the cat, it's just superposition. It's both dead and alive at the same time because there's a possibility of both. Qubits in a quantum computer behave really similarly. They don't settle on being a 1 or a 0 until you measure them. Instead, they exist in a blend of both states. This ability to hold multiple possibilities at once is what gives quantum computers their incredible potential for parallelism, which allows them to explore many solutions simultaneously. Some of the most famous quantum algorithms include Grover's search algorithm. This allows quantum computers to search through databases exponentially faster than classical ones. So if we're looking through a phone book for a name, instead of going page by page, it looks at every single page at once. For Shor's algorithm, that's another algorithm that can factor really large numbers incredibly quickly, which threatens to break modern encryption methods. It's one of the reasons that quantum computing is so significant in cybersecurity. These algorithms act as blueprints, which guide the design of quantum circuits. The circuits are then fine-tuned to perform specific tasks like optimization, simulation, or even creative problem solving. In the TikTok, we talked about how Willow, Google's quantum chip, solved a problem in just 5 minutes that's so hard it would take the world's fastest supercomputer over 10 septillion years to solve. But what kind of problem was it? It was a quantum circuit. In computer science, circuits are models of computation where information is carried by wires through a network of gates that transform the information carried by the wires. Quantum circuits work similarly, but with an added twist. They have the unique properties of quantum mechanics, like superposition and entanglement. This allows the problems to be far more complex than classical circuits. It's a bit abstract, so let's make it more concrete. The best example I could think of, I just binged them all on Netflix. And in their challenges, they get a portion of a map and clues to figure out the rest of the treasure map. Maybe this was inspired by quantum circuits, maybe it's just a coincidence, but either way, imagine you're on a treasure hunt and the map isn't complete yet. The qubits, the 0, 1, or the 0, 1 in superposition, are like the blank pieces of the puzzle of the map. They start off holding all of the possible answers at once. Right now, the treasure could be anywhere. So the quantum gates are like the clues that you uncover along the way. Each gate gives you a new piece of information or rearranges the puzzle pieces, which brings you one step closer to solving the map. And when you measure all of the qubits together, all of the possibilities together, it's like putting the pieces together to reveal the completed map, which shows you the location of the treasure or the solution to the problem. So one other question I got was, who designs the quantum circuits? Quantum circuits don't appear out of thin air. They're designed by teams of brilliant minds. Physicists, mathematicians, computer scientists are normally at the forefront, collaborating to create algorithms and equations that quantum computers can use to tackle real-world challenges. For Willow specifically, the development was led by the Google Quantum AI team, which was founded and led by Hartmut Neven. Julian Kelly, the director of quantum hardware at Google Quantum AI, also played a significant role in development. The team also includes physicists, engineers, and computer scientists that all work together to design and implement the quantum circuits and algorithms. While the exact individuals behind the circuits haven't been publicly disclosed, the team's collective expertise was instrumental in achieving this groundbreaking performance. All right, so back to overall. Quantum circuits don't exist in isolation. They're built to solve specific challenges, hopefully real-world challenges. Tech giants like Google, IBM, and Microsoft, along with leading academic institutions, design benchmark problems to test the capabilities of quantum computers so then they can be used in the real world. One of the most exciting areas, I think, is drug discovery. Traditional computers struggle to simulate the molecules at the quantum level, where tiny interactions between electrons and atoms play a huge role in how molecules behave. Quantum computers can handle these calculations with incredible precision. They can model molecular interactions that were previously impossible to simulate. Imagine being able to design a new medicine in months instead of years, significantly bringing the cost down for life-saving treatments to get onto the market. For example, quantum computers can help researchers identify the best molecular structure for targeting specific diseases like Alzheimer's or cancer, or even create new materials for more efficient drug delivery systems. Quantum computing could revolutionize how we tackle global challenges like climate change. For climate modeling, quantum computers can process massive amounts of data about weather patterns, greenhouse gas emissions, and atmospheric changes. And it could help create more accurate and detailed simulations on how our planet is evolving. This level of insight could help guide policy decisions and even help us mitigate the events of climate change more effectively. In logistics, quantum optimization is a game changer. Companies like FedEx or Amazon can use quantum computers to find the most energy-efficient delivery routes, cutting costs and reducing emissions. It's not just packages, though. This kind of optimization applies to public transit systems, airline schedules, and even energy grids, making operations greener and more efficient on a global scales. But quantum computer isn't perfect. Far from it. These machines are still in their infancy and face several challenges. For one, they're very fragile. Even tiny disturbances like heat or electrical noise can cause errors. To avoid this, they must be kept at temperatures colder than outer space, using specialized cooling systems that are expensive and really complex to maintain. On top of that, for some fun facts. First, for many tasks, your laptop is still faster than a quantum computer. It's not about being faster overall, it's about solving problems classical computers simply can't handle. For data, quantum computers can't just copy and paste, can't Control-C, Control-V it. This is due to a quantum rule called the no cloning theorem, which says you can't perfectly copy a quantum state. In 2019, researchers used a quantum computer to reverse time on a particle simulation, effectively undoing an operation. This is something that classical computers can't really replicate. Oh, quantum teleportation is real. Scientists can transfer the state of a qubit from one place to another without physically moving it, thanks to quantum entanglement. But we're not transporting humans just yet. Ooh, for randomness, unlike your phone's random number generator, or like when Spotify's on shuffle and you can already start humming the next song, quantum computers generate numbers that are truly random, thanks to the unpredictability of quantum states. Oh, which side? It's on this side. As you can see here, quantum chips look like golden chandeliers because of the intricate cooling systems and wiring. They're as beautiful as they are complex. Einstein wasn't a fan of quantum mechanics, famously saying, "God doesn't play dice with the universe." Today, quantum computers are proving just how dicey the universe really is. Quantum computers can rewrite physics. They're not just for solving problems. Quantum computers can help us discover entirely new laws of physics by simulating systems we've never been able to study before. The quantum world is tiny. Last one. Qubits can be built using particles smaller than atoms. So when you hear quantum computing, it's a big idea, but physically, think really small. To recap, quantum computers use qubits and quantum circuits to solve complex problems by exploring all possibilities at once. The equations and problems come from brilliant minds in physics, math, and computer science, and they're already transforming fields like in medicine, logistics, and more. If you have any questions about any other science topics, drop them in the comments. I would love to talk about them for future episodes. Thanks for listening to Minute Science Marvels, and I'll see you next week for another deep dive into the wonders of science.